Alright, here we go. So solving trigonometric equations. That is what we're doing today. You should go on page 36 along with the goal. By the end of today, maybe a little bit into the next class, you guys are going to be able to solve trig equations using algebraic techniques as well as basic trig identities, okay? So we're basically going to be solving, dealing with trig. In order to be successful at this, you need to know your unit circle, okay? I've been kind of saying this for a while, like we're just not done with unit circle just yet, okay? So you're going to be coming back to the unit circle, okay? So if you've already forgotten it, then you probably might want to flip to the page that has your unit circle on it. We are going to be referring back to it. However, if you do know about it, then you're good to go. So looking at our bubble that we just created, when solving trig equations, a trigonometric equation is an operation that contains a trig expression with a variable, such as sine x, okay? Now, an equation is something with an equal sign, okay? And make sure, guys, you're only filling in 3 words here, so stay with me as I go through each definition, okay? So you should only have the first thing written down. So, and this is an equation. So it's going to be something like sine x equals 1, okay? Or cosine x minus 2 equals 3. Something like that, okay? That is a trig equation. Now, identities, we already know, such as sine x squared plus cosine x squared equals 1 is true for every value of the variable. We talked about identities for the last 2 lessons, you guys. You know, you already knew that's what it was. We even verified them. We proved that the left side could indeed equal the right side. That made an identity. So the solutions are the values that satisfy the equation. These are the ones that, you know, you plug in the value and that's what makes the equation true. Okay? So if you have something like sine x equals 1, when you solve it, you're going to figure out what is the angle, what's the radian measure, or what's the degree measure that when you plug it in and you do the sine of that angle, you get 1. And just out of curiosity, where on the unit circle is sine 1? Yes. Yes, it's pi over 2. It is pi over 2. And so basically the solution here would be x equals pi over 2 because when you plug pi over 2 in, sine of pi over 2 equals 1. Yes?
Wait, I think
So we'll begin by finding the revolutions for the solutions for one revolution. So one revolution is in between 0 and 2 pi. And then we'll expand it to find the general solutions of these equations, okay? General solutions are things like 2 and pi, pi n, etc., okay? So you can use these different techniques when solving an equation. Some of them are very similar to when you're simplifying them. That is collecting like terms, using the square root method. You know, that's when you take the square root of both sides. Factoring. The quadratic type, you know, where you're dealing with some quadratic equations, and you're, you know, figuring out, you know, what 2 numbers multiply to give you this, that adds to give you that. We're also going to be using our identities to help us maybe simplify something to solve. And then, of course, general solutions. And last but not least, squaring both sides. Now, that last one, you don't use too often. You usually use it when you're given 2 different trig functions. You can't use an identity for them, and you can't factor anything out. That's when you kind of go to that. That's like your last resort to solve a trig equation.
turning it into sine to do sine.
Yeah. Yes.
I remember my question. I'm like, if you have something like where does sine equal 0, how do you know which one it is? Like cosine equals 0.
Okay, that's a good question. So ones that have multiple answers, you're just going to provide all of them that fit in the particular restriction that we have, right? So if the equation was sine, like you said, sine x equals 0. Well, sine equals 0, and technically from 0 to 2 pi, it equals 0 at 0, pi, as well as at 2 pi. So all 3 of these would be your solution because they all fall within that interval. So some of these may only have 1 answer, some of them may have multiple answers. But the one thing you don't want to do is you don't want to leave out an answer if it is to be an answer.
Okay.
You understand that? Okay. So let's get to solving. One way to solve is, of course, graphically. Okay? Now, will you use this one? Probably not. Okay? Especially if it's a value that's not necessarily on your unit circle. Okay? Do you guys remember where sine crosses the y-axis? At 0, 0, and then it goes from 0, 0, it goes up. It goes up to what value? 1 at
pi over 2.
Pi over 2. And then from there, it does what? Goes down to 0.
Goes down more.
Goes down again to 3 pi over 2, and then comes back up to 0. And that is one cycle with a period of 2 pi. What if I want to go to the left? Go down, up, up again, and then down. Okay? And of course, it does keep going beyond negative 2 pi and beyond positive 2 pi. Okay? So it doesn't just stop there. Now, when we solve this graphically, what you do is you graph one side of the equation, you graph the other side. This is basically y equals 1/2. Y equals, what does that look like? What type?
Horizontal.
Horizontal line that crosses the y-axis at 1/2. So, I'm going to draw that in. Not my best horizontal line, but you guys get my point. And then the solutions to this would be where the two curves intersect each other.
Like the asymptotes for the other things.
Exactly. It's kind of like the asymptotes for like the tangent function. They happen in multiple places, okay? It just doesn't happen just at these two places here. It also happens here and here. And if we kept it going, it would happen here and here and so on and so forth. So there are multiple solutions, okay? That's when you would write a general solution to represent all of those, okay? Now, using your unit circle, where does sine equal 1/2?
Pi over 4.
Ooh, we had all three from the first quadrant. Which one is it? It's going to be pi over 6. Remember, it's the y value. Where's the other place where it is 1/2? Now, negative pi over 6 will be here.
3 pi over 2.
Now, 3 pi over 2.
5 pi over 6.
It is 5 pi over 6. Okay. Well, go rusty on the unit circle.
That's not even unit circle. That's something else.
No, that is unit circle. Because remember, in your unit circle, every ordered pair that you have, the x value is the cosine, the y value is the sine. Okay? So, those would have been your two solutions that you would put if we were restricted from 0 to 2 pi. Since we don't have restriction here, we need to list all of them. Okay? So, it hits here, it hits here. It doesn't happen again until it passes 2 pi and then hits again here. This is the same point that this is, just after one full revolution. Does everybody understand that? It's like, here is pi over 6, and then this point right here that I'm going to label in purple is the same angle, just gone around one more time. That's a full revolution. That's a full how many degrees? Or how many radians?
2 pi.
2 pi. So that's going to happen every single time. It's, as long as we keep going around and going around and going around, this will always be where sine equals 1/2. There is one in between them, but we'll worry about that later. Okay? But to represent every angle, that pi over 6, that 13 pi over 6, that all those angles that hit right here, our solution would be pi over 6 plus 2 in pi. It's like what we did when we wrote the asymptotes. We found one of our asymptotes, and then we determined how far apart they were. Same thing. We found where it hit, 1/2, and then we figured out how far apart they were, which was 2 pi radians. That is a general solution. Okay? The other angle was at 5 pi over 6. And it will always hit there, no matter how many revolutions it is. I can keep going and keep going. How would I represent that solution? Exactly, 5 pi over 6 plus 2n pi. Because that solution happens every 2 pi radians at the same point. At the same point. Questions? You guys don't have to draw this one in. We're going to solve this one as well by graphing. We're going to solve this one as well by graphing. Okay? Now, we can do this one of two ways. We can get it to where it's just cosine equals something. Or we can graph it the way it is, because you guys did learn how to graph an equation that is 2 sine x minus 1. You guys tell me, how do you want to solve this? Do you want to graph what we have over here? Or do you want to get it to where cosine is by itself? Where cosine is by itself, okay? So to get cosine by itself, what do I need to do? Add 1 first. So it's going to be 2 cosine x equals 1, and then? So now that we have cosine x by itself, it equals 1/2. So we're going to graph two things here. We're going to graph the graph of cosine, and then we're going to graph the line y equals 1/2. Where does cosine cross the y-axis? At 0, 1. And then from there it goes down, and then down some more, up to 0, back up to 1. What about here going to the left? Is this reflected? So it goes down, down, up, up. And of course it keeps going, because this is a continuous type of function both ways. We'll graph 1/2. That's again just another horizontal line. How many solutions are there going to be? Infinitely many. So that means you're going to be writing a general solution. Okay? So it intersects here and here. This is where you start. You see where exactly those values are from 0 to 2 pi, and you use your solutions based off of that. What is this value right here?
Pi over 3.
Pi over 3.
Wait, how do you know?
How do you know, Luke?
Because it's asking where cosine equals 1/2. So it's
Oh, yeah.
So you're looking for where the x value is that. So it's pi over 3. What's this value here?
3 pi over 2.
2 pi over 3.
Say again?
2 pi over 3.
Now 2 pi over 3, that's a negative 1/2. I'm looking for a positive 1/2. Where does cosine equal a positive 1/2?
Pi over 3.
No. That's what I said.
You said 2 pi over 3.
Oh, yeah, I did.
Okay? So that right there, those are just two of the solutions. But how do you represent all the solutions? What do you have to add to both of these?
Pi over 3 plus 2. Oh, it's
2 and pi. And if, before anybody says it, will that always be 2 in pi? Yes, if you're dealing with a sine or cosine function, because that is the period. That is the period. The tangent, does anybody remember what the period of tangent was?
It was like,
And how far apart is that? How far is that? Pi. Huh? So the period for tangent was pi units. So if say this was a tangent one, your solutions are going to be separated by a pi instead of 2 pi. So those would have pi in instead. Okay? Questions for these? Alright. I'm more concerned about the ones like this where you actually got to solve it by hand, okay? No need to worry about graphing. Collecting like terms is one of the ways, one of the strategies, okay? collecting like terms, that means getting everything on one side, getting all your signs on one side, everything else on the other side. How do I do that? How do I get my signs on the same side? Do it either way. Add sign X or subtract sign X. Doesn't really matter. Okay? We'll go this way. So, that cancels out. We're left with a root 2 on the left side. What are we left with on the right side? Alright, now our goal is to get sine by itself. -2. So we have sine x equals, and you guys, just because it's a negative in the denominator, it technically makes the entire fraction negative. So that's a negative root 2 over 2.
Wouldn't that be 7 pi over 4?
That would be 7 pi over 4. That's one of our solutions. Where else is sine a negative root 2 over 2?
7 pi over 4. Yeah.
So these are your two solutions here. If we were bounded between 0 and 2 pi, you would stop there, and that'll be it. But it doesn't say that. So we need to write our general solutions. What do I need to add to both of these? Plus the 2 and pi. If you said 2 pi and 2 and pi, they all mean the same thing. Are we good? Okay. So knowing that unit circle can be very helpful. Let's look at this one.
Uh-oh. You have two trigonometric functions. Do you have to be different for you to have to use the last technique? Or is it always the...
And where we can't use an identity. Like I'm talking about that. Okay. Wait, how should I start this one? Subtract 14 cosine x. And realize, guys, that x is attached to the cosine. So you just can't subtract negative 14 cosine. You gotta take the x with it. So what's 18 minus 14? So you have 4 cosine x minus 7 equals negative 5. Add 7. It's your old school rules of solving equations. It's just now, instead of it just being an x, it's a cosine x or a sine x or a tangent. That's 2. We divide both sides by 4. Wait, hold on. Wait, 1/2. Don't be jumping. Okay? Baby step. Okay? So then you ask yourself the same thing. Where does cosine equal 1/2? And? Okay? We're not restricted from 0 to 2 pi, so we have to...
Tell me, isn't there 3? Oh, just kidding.
Now, sometimes, guys, and Isan and I have already kind of had this conversation already. It won't always be 2 solutions, okay? It might be 1. It might be 4, okay? But you want to make sure you list all of them. Yes?
For the 2 and pi,
Yes?
it can be in any order because they're all being multiplied, right?
Yes?
Isn't cosine x?
Yes?
So how would it be 2 pi over 3 pi negative? Equals a negative.
Thank you. It is a negative. So let's fix this.
That's what was confusing.
5 more 2 first.
So it would be 5 pi over 3.
5 pi over 3. Yes, thank you. A positive 1/2. Not a negative. Positive.
So both
Both of the angles that we start with have to be positive. Yes. Okay? Wonderful. Various techniques. Okay?
Is there no solution to this problem?
Huh?
Is there like no solution?
Maybe, but still that won't get there. I don't think any of the ones for today are no solution. Okay? So, various techniques, okay? The next 3 examples are going to be ones that you use different techniques for, okay? So let's go ahead and go to example 5. You do have to write this one in. We have 4 sine x squared plus 1 equals 4. Anybody have a suggestion how we can work this out? Like, subtract 1. then divide by 4. Square root both sides. This right here is using the square root method.
And we know that we're signing equals root 3 over 2.
Now there's one thing that you gotta remember when you take the
Plus
square
minus.
when you take the square root, it's plus or minus. Well, we don't have that restriction of telling us that we only want the positive numbers or only the negatives. So when we do this here, we're going to have the solutions where sign is a positive 3 over 2, and then where sign is a positive square root of 3 over 2, and where sign is a negative square root of 3 over 2. Let's start with the positive ones, okay? Where is sign a positive square root of 3 over 2?
Sign is y.
Yeah.
Sign is y, so that should be pi over 3. And where else is sign positive?
7 pi over 6. No. 5 pi over 6.
Wouldn't it be also number in the denominator?
3 pi over 6.
5 pi over 6.
Oh, that's a negative.
2 pi over 3. Okay, that's where sign is a positive square root of 3 over 2, because remember, sign is your y coordinate. Where is it a negative? That would be third and fourth quadrant.
It's
5
4 pi over 3.
4 pi over 3.
That's it.
One more.
5
5 pi over 3. Hey, a quick trick. If you figure out that the values are here and here, they correspond to the same ones.
Oh, so they should all have the same denominator.
So the 3's are the closest to the y-axis. The 6's are closest to the x-axis. That's even better. What do I need beside every single one of them?
Plus minus.
Plus the 2 and pi. Now, one thing I will say. Okay? This is totally acceptable as an answer.
Would it not be a minus? Or would it just have a negative in front of the 4 pi?
If we can make n a negative, and then that would be like subtracting 2 pi, so we get the negative ones. One thing that we can say, since we are including all 4, okay? These 2 right here, how far apart are they? One what? Huh? They're 1 pi apart from each other. Like, think about it. If you do pi over 3 plus pi, you add those together. What do you need?
5 pi over 3.
Common denominator, that'd be a 3 pi over 3. What's pi plus 3 pi? Wasn't that one of our solutions?
Yes.
Okay, so what we have here in the black and the red, that's totally acceptable. Another solution that would be acceptable, the more simplified solution, would be x equals pi over 3 plus n pi, and then also 2 pi over 3 plus n pi. Exactly. Like if we only go half a revolution from any of our answers, we'll end up at a corresponding answer. So either what's in the black and the red, that's an acceptable answer. A more simplified answer, a multiple choice answer would be that. Okay? A very heavy hit.
So can you always simplify the 4 solutions to 2?
If they are separated by a pi gradient, yes.
And the pi will never change. It won't be like half pi or anything. It's always going to be pi. Yes. Okay.
Questions? Okay.
That calculates pretty fast.
Let's take a look at this one. So this one. Subtract 4. Divide by 3. So we're basically isolating, getting that by itself. Cotangent squared x equals 1. We're going to have to what? Take the square root, and remembering when we square root, it is plus or minus what's the square root of 1? 1. Now, do you know your cotangents off the top of your head? Okay? I mean, you can from here, you know, we know cotangent is what over what? Cosine over sine. X over y. So we could figure out, okay, where exactly is it when I divide my x by my y, I get a positive 1 or a negative 1? Oh, we already got some answers. Okay. It's pi over 4.
Square root of 2 equals 1.
In order for us to get 1, that means that the x and y coordinates are going to have to be the same thing. That only happens here. At pi over 2, the order pair is 0, 1. 2 pi is 1, 0. 3 pi over 2 is 0, negative 1. When you divide them, cosine over sine. So if you divide any of these three right here, you're either going to get a 0 or undefined. We're looking for a positive 1, which means that the ordered pairs would have to be the same. And negative, yes.
Can it be x over y?
It would be x over y, yes.
So we do 1 divided by 0 for 1.
1 divided by 0 is undefined. The 0 is on the bottom. So we also going to have 3 pi over 4 and 7 pi over 4. Okay? But cotangent is the reciprocal of tangent, which means its period is the same as tangent. What's the period of tangent? Plus pi n. Now, when you add a plus pi n, what's pi over 4 plus pi? Pi over 4 plus pi. 3 pi over 4. That's one of our solutions already. When I add, actually no, that's not 3 pi over 4, it's 5 pi over 4, I'm mistake. When I add a pi n to a 3 pi over 4, you get 7 pi over 4, so you get your other two solutions. Okay? So if you yourself were writing this out and you put all 4 of these solutions plus a pi n, that's fine. I wouldn't count you wrong. But these two right here would be your more simplified answer, because if we add pi, we get the other two solutions. The ones that are boxed would be your multiple choice answer. Does everybody understand that? Strong hand. Your multiple choice answer. Yes, the test for this particular section is multiple choice. Okay. Strong hand.
Strong.
Yeah, so in other words, what's the simplified version?
No. Like from a scary movie?
Oh God, no. Get your mind out the gutter. Questions? No questions? Let's do another method. And oh my goodness, on this one, I need you to put this in the margin because I know it's going to happen. You at home watching this video, please make sure you make a note of this in the margin. You cannot divide both sides by a cosine x. You cannot. Because when you do, you lose a set of answers that are correct to this equation. So do not divide both sides by cosine x. If it was the sine x over there, don't divide by sine x. If it's the same trig function on the left and the right, do not divide. Yes, ma'am.
Okay, so don't divide.
Divide by cosine x, sine x, and the cosine cross out?
No. Not here because they're
multiplied though.
they are multiplied, but
If you divide by the whole equation, don't do it with cosine cross out?
yeah, the cosine would cross out, but that's the thing, you would lose a solution that goes along with the cosine. This one you wouldn't be able to simplify none. But you can factor. If you bring the 3 cosine x over to the other side by subtracting it, cosine x. I think we did this at one time with simplifying, where we had the two terms had the same thing in common. We factored it out to try to simplify it. We can do the same thing here when we're solving. We'll have a sine x minus 3 equals 0. And if you remember back from your factoring days that when you have two factors, you set both of them equal to 0. That's using an old property called zero product property.
Whoa, that's long.
So you'll have sine x equal to 3. And so basically what you'll have is you'll have two different equations that you're solving for, but the solutions you get are the solutions for this particular problem. So let's start with cosine x. Where on your unit circle is cosine 0? Pi over 2 and 3 pi over 2. Ooh.
If you add a pi.
If you add a pi, don't you get 3 pi over 2?
Multiple choice.
So here's your multiple choice answer. Pi over 2 plus n pi. Now if you said pi over 2 plus 2 n pi and 3 pi over 2 plus 2 n pi, that's fine, that will be okay, but the more simplified answer is that. Now this one, where in the circle is sine 3?
No, that's not.
Say again? There's no such thing. Because what's the highest that sine goes? 1, negative 1 to 1. So anytime you get a sign that's outside of negative 1 and positive 1, you're not going to have a set of solutions for that. So this one is your only
Wait,
answer.
so what's negative power 2 power 2? That's the sine inverse.
That's the inverse, yeah.
So,
I got that right on my test.
They do like revolutions.
Because it's like where does that graph go up to? Like so sine should go up to positive 3, but it doesn't. It only goes up to positive.
so basically, if we would have divided it, we would have gotten the two answers we were supposed to have wrong.
Correct, because if you divided both sides by cosine, you would just been left with sine x equals 3. There are no places where sine equals 3, so you would have said this was no solution. When in actuality, there are solutions.
I thought there's 3 cosines there. So when you're dividing by, oh no, without being added, so you.
Questions? No, you won't get this one wrong.
On the retake.
Oh.
Yeah. See, I will
You guys didn't finish the rest of these at home?
Mm-mm. We're gonna get through a good amount of them.
Oh yeah, I know.
All right, so here we go. We're on equation 8. Okay. Now these are the ones that involve identities.
Uh-oh.
Okay? Now, this is one of those strategies. When you get a particular problem, you look and you see what trig functions are involved. This one has a sine squared x, and then we have a cosine x. One good rule of thumb is to try, if you can't like factor out a common factor like we did in the last problem, rewrite this so that they have the same trig function. Instead of you said what?
Wouldn't it, since it's being times by 2, wouldn't it be, well, you can do 2 parentheses 1 minus cosine squared x equals 2 plus cosine x.
You can use that Pythagorean identity to replace sine squared x with a 1 minus cosine squared x. And by doing that, you now have one trig function that you're working with instead of 2 different ones. Okay?
Did you divide cosines by 2?
That's what I was thinking.
You could have sine squared x and then
You have to divide the cosine and the 2.
You have to divide the cosine as well by 2.
So you have
So then you have
cosine.
one half cosine.
Oh no, 2 don't cut out.
Alright? Let's how about this? Let's distribute over. So when I distribute, I get 2 minus 2 cosine squared x equals 2 plus cosine x.
And then you would have to do that.
Right? Now we can't divide. I mean, we could divide by 2, but then we would have to divide the cosine as well by 2, and that would leave us with a 1/2 cosine x. Instead of doing that, let's bring everything to the same side, because this is a quadratic here. And then factor it. So let's subtract 2. Ooh, what happens?
They don't cancel it, did it? Okay,
And Let's subtract over cosine x.
-3.
Nope. Are these the same?
Oh, no, they're not.
So this is a -2 cosine squared x minus cosine x equals 0. Let's pause right there for a second. What can I do from here? Factor of what?
Negative cosine x.
It could be in your benefit to factor out a negative cosine x. Just be careful. When I take a negative cosine x out of a -2 cosine squared x, what am I left with? A positive 2 cosine. When I take a negative cosine x out of a negative cosine x, positive 1.
Man,
Because you always need a placeholder.
remember that 2 is still there.
Remember that 2 is still there, and when you do, if you end up factoring out one entire term, you still need that placeholder there.
Does it matter if you would have just took out a regular cosine?
Mm-mm. If you took out a regular cosine, then both of these would have been negative, and then you'll just have the negative to deal with when you set them both equal to 0.
Just one.
So let's set them both equal to 0.
What method is this?
The 0.
This is using the quadratic formula and using identities. So the combination of 2 and 1.
Oh, 2 different equations.
Mm-hmm. So you have cosine x equals 0, and then cosine x equals a negative 1/2.
I already read it.
Wait. Couldn't you say since there's a negative cosine, wouldn't it be -1 cosine x? Okay, yeah, that's what it would be.
Alright? Add this in. We're going to only do the solutions between 0 and 2 pi. I think you guys got the idea of doing the general solutions, right? We did 7 problems worth of general solutions. We're good, right? Okay. Let's do it just on the regular unit circle. Where is cosine equal to 0? Pi over 2.
Power 2 plus n.
Oh, we're just doing on the unit circle. I added that in. I think you guys got the idea, right?
Mm-hmm.
So here are 2 solutions here.
So general solution is the default unless you give us the period.
Right.
Okay.
Wait, what?
Restriction. He said general solution is the default. So in other words, you write the solutions as general ones unless I tell you otherwise.
And that's telling us otherwise.
Right. So this, we are only looking for the solutions that are on the unit circle. Yes?
Okay, could, like for multiple choice answer, could it be pi over 2 plus n? Or plus pi instead of plus
That's what I'm
n pi?
trying to figure out.
Say it again.
Could it be like for this one, pi over 2 plus n? Or plus pi?
Oh, no.
It wouldn't be that.
If it was restricted like this, it would have both solutions.
Okay.
When you say restricted, that means you don't want the equation?
I don't want the equation. I just want these right here.
Okay.
Because you're only looking at the line of revolution.
Correct. I'm only looking at the unit circle, not beyond it. What about here? Where does cosine equal a negative 1/2? 2 pi over 3. You said 4 pi? So you have 4 solutions here. Now, also don't get it twisted. A multiple choice test could only have 2 solutions, not all 4. Okay? So do be aware of that. Make sure if you find all the solutions and you pick the answer that has all the solutions. All right. All right, here we go. Oh, yes. I have several. Let's not get twisted. I have several.
What? Whoa,
No,
just
factor.
come on. We have like 10 minutes left.
You act like it's going to take a long time.
Factor, bro.
Yes. And I want to bring up this way of factoring because students tend to forget it. Okay? Yes. Factor by grouping. Students tend to forget grouping. Okay? And what you should recognize is that you can't just regularly factor this. Okay? You can't.
Just take out a 2, don't you?
Well, not every term has 2. What you
Not
do,
funny.
you have to subtract the 2 over first to set it equal to 0. So whenever you factor, you always want to make sure that it's equal to 0.
And the fact that there's no like multiplication sign is so aggravating.
Huh?
Like there's no multiplication sign, so it's like
Just make one.
Okay? And then factor by grouping. Remember, factoring by grouping, you group the first 2, You group the last two. What's the GCF of the first group?
You can take out a secant, no.
Take out a cosecant squared x. When you do that, what are you left with? Plus
2.
2. What's the GCF here?
A negative.
A negative 1. When I take a negative out of here, this turns into a what? Plus 2. And remember, when you're factoring by grouping, the 2 inside should be the same. So here's my factors. Cosecant squared x minus 1 and cotangent squared x plus 2.
Where did the cosecant squared come from?
That was the GCF from the first group.
Oh, okay. Yeah.
Okay?
So then what do you do? Oh, I didn't break that. I see. Yeah, that would be negative n. No, wait.
Hold on. Here we go with this. So from here, you would set them both equal to 0.
Well, CSC is undefined. Isn't it? No. Oh, yeah.
Yep, move the 1 over. Take the square root. And remember, when you square root, it is plus or minus 1.
Teachers, at this time,
Okay, so we have cosecant x equals a positive or negative 1. You guys, if you're like, I really don't like working with cosecants or secants or cotangents, what's the reciprocal of its sine? So to get sine, all you have to do is split this. When you flip 1, what do you get?
1.
So you're really looking for where sine is equal to a positive or negative 1. And again, I'm going to restrict this only on the unit circle.
Pi over 2.
Sine equals that at pi over 2 as well as, okay? Over here, you have cotangent squared x equals a negative 2. How do you solve this?
Close over sine.
Take the square root. When you square root a negative number, what happens? You get an imaginary number. Are there imaginary numbers on the unit circle? No. So your only solutions are the ones right here.